let me see. So actually, this worked better with the notes, so I actually just shared this screen. So just because then, no, it's fine, because then we don't have to worry about all this. So this should be fun. Let's do that. Is that cool? Good. Okay. You travel. Do you need a laser? Yeah.
I have a laser. Just make sure that this is the right. Oh, I know.
Okay, so this is the last lecture of the school. And last but not least, I'm happy that Sara was able to come. Sara Haravifard from Duke. And please, without further ado.
Thank you. So thank you very much. I'm really glad to be here with you. And so today I'm going to talk to you about my take on the challenges that we face when we talk about frustrated magnets and the exotic phases that comes from that. Something.
Yeah.
Okay. So as you can see that I'm talking about the complexities of frustrated magnetic systems. And I would like to, so you have heard about this, I'm sure, during this workshop a lot at the school. So I will just go through this as a reminder of what are the things that we know about frustrated magnetism, the techniques that we typically use to probe them, and then what are the challenges and how we can mitigate those challenges.
Go ahead.
Yeah, okay. Good. So when we talk about frustrated magnetism, if we step back and we think about when we have from our textbook quantum mechanics lectures, if you have two spins, let's call them quantum mechanical spins with a spin and a half, then you start to think what kind of interactions is going to be coming out of this type of interactions. So first, if you think about it, if you have two spins with spin and a half, you can have either a singlet ground state or you can have a triplet ground state, right? So there would be these two very unique properties of these two spins that are going to be interacting with each other. Now, things becomes interesting when you basically try to decorate a particular lattice or a particular symmetry of these spin halves, okay? So one thing is that if you are in 3 dimension, things are a little bit more trivial, but still you have many body interactions and things can become very complicated. But things are becoming even more interesting when you reduce the dimensionality of your system. So if you go from 3 dimension to 2 dimension and 1 dimension, according to Wagner-Merman's theory, you're going to have a situation that no matter how hard you try and how low in temperature you go, your system does not want to get to an ordered state. So if you have a magnetic system, which is a 3-dimensional system, when you cool it down, what it wants to do, it wants to minimize its energy. And typically that happens when the speeds start to order. And when I call order, I typically mean long range order, okay? So it does want to get to a long range order, and that typically happens unless you have frustration in the system. Now, if you go to 2 dimensions though, even if you are not having as much frustration or the frustration factor is not going to be as high, just reducing the dimensionality according to the theory is going to put you at a border between an ordered state and a disordered state, okay? And in 1 dimension, it typically doesn't, it wouldn't be able to order at all. So when these things happen, what you're going to deal with is basically quantum fluctuations, because we cool down the system, so you don't have a lot of thermal fluctuations, but you do have quantum fluctuations that play a key role. That's why lower dimensional systems, specifically in frustrated magnets, are very key for us to understand exotic phenomena that comes out of quantum mechanical realm, okay? Now, when we talk about magnetism, this is basically your ingredients, right? So I always tell this to my students that working on a new sample or trying to design a new compound is basically like cooking. So if you want to cook something, you want to see what kind of a flavor it has. Is it going to be vegetarian? Is it going to be meat-based? Is it a steak or whatever? So you have to have an ingredient base, and based on what you would like to probe, you can pick and choose what to basically put in your design or in your recipe. So if you look at the ingredients that we have, it's actually quite rich, right? Because you're having these d orbitals that are basically, most of them are going to be magnetic materials, and also you have the rare earths that they also have magnetic moments, right? So there are differences between these two, though. We have to be careful. So when you're dealing with a d orbital versus an f orbital, then you have crystal electric field interactions, you have spin-orbit interactions. So for each of them is going to be different. So for the, for example, for the 4f electrons, you're going to be very careful about the crystal electric field excitations, okay? So overall, we have this type of ingredient table that we can pick and choose and then put on, and then when we design that, we would like to put them on a particular lattice. And those lattices, depending on how they look, is going to give us different properties. So what we said was that these spins need to talk to each other, okay? So when you're designing the material, the spins are going to be talking to each other, and there are main two, so there are other ways that they can talk, but the main two ways that they talk to each other is through either exchange or through what is called an RKKY interaction. Okay? So this exchange is mainly what we focus on today, and this is basically for most of the insulator compounds. But if you have a compound that's metallic or it has charge carriers, then you can see that these charge carriers can actually, so here are my spins that are sitting, and I have decorated, for example, in a chain, and then the interactions in the case of RKKY is going to be these mobile electrons that they can see what kind of interaction this spin has, act as an agent, and then tell to the next site that, okay, you have to be ferromagnetic. In case of an exchange interaction, you basically can write them the Hamiltonian, but then depending on what kind of an interaction it has. So that interaction comes from the fact that you're going to have some sort of a bond between these magnetic ions, right? You can have oxygen, you can have chlorine, you can have, and that angle is also going to be very important. So the way those orbitals are going to make an angle with each other and who's the agent between them is going to tell us either you have a case of a ferromagnet, antiferromagnet, and how strong those interactions are going to be. Okay? And then again, if you're going to have a preferred orientation, then your Hamiltonian is going to be, for example, written in a way that you have only Ising spins. So your spins are going to be basically pinned along one direction, or you can have a Heisenberg type of interaction where the spins can actually move around. They can still be ferromagnetic or antiferromagnetic, but the orientation of the spin is not pinned to a particular direction. Okay, so frustration, right? So frustration, which I typically tell my students that I'm very frustrated when things are not frustrated. So it's typically what we want for our systems to be very frustrated, and that would give us very rich physics. So the way that you can think about it is either through geometry. So if you can have, for example, your motif is going to be a triangle. I'm sure you have seen this 100 times. So if you see in a particular case of a triangle, and if you call the exchange interactions between these sides antiferromagnet, so my J is going to be antiferromagnetic interaction, and what is also important is that if you have an Ising type interaction, so your spin won't be able to rotate around too much, but they would be able to pin up and down with respect to each other. So in that case, what you're going to have is that if this spin is up, it's telling this side to be down, and then this side is going to look at this side, it want to turn down. If it's looking at this side, it's going to turn up. So this is going to be frustration. So that's that frustration, or that basically degeneracy of the ground state is going to be what is going to give us a lot of rich physics. However, so you can actually use this triangular motif to make different type of lattices. You can have a triangular lattice. You can have, we just had this talk about, fantastic talk about the Kagome systems, right? So you can have a Kagome system. But also, you don't have to necessarily have the geometry to induce frustration. Sometimes the frustration can come from the fact that you're going to have competition between different interactions, okay? So for example, if I look at the square lattice, and in this square lattice, I'm going to call this spin, the spins again are going to be antiferromagnetic, but then there's going to be some sort of a competition between the sites. So you're going to have the nearest neighbor sites and next near neighbor sites, and if these interactions start to compete with each other, then you're going to have, again, frustration. And these frustrations in these type of systems, there's a very famous way that you can look at it, is basically a chassis-Sutherland system, which these days is becoming very, very topical because it can host altermagnetism, if you have heard about that word. So anyway, so what I'm trying to say is that frustration can come from the geometry or can come from the competition between different sites. Okay. Now, when we talk about the frustrated systems, one of the key and one of the most important consequences of that is quantum spin liquids. So quantum spin liquids are basically very interesting state of matter, and there are different categories to quantum spin liquids, but the point is that it is so on paper, when you look at the theory, it is beautiful, and they describe different basically groups of quantum spin liquids, and in basically in 1973, Anderson, the first time, he mentioned that there's going to be this resonance valence bond which induces the quantum spin liquids in triangular lattices, and then again they also actually mentioned that there's going to be also some sort of a connection between the quantum spin liquids and unconventional superconductivity. So it's important, and it does have very flagship type of characteristic. So one of the main characteristics is that your quantum spin liquid is one of those frustrated systems that doesn't want to order. So its ground state is very much disordered. Even though the ground state is very much disordered, what actually happens is that that disordered state is also having a very much strong entanglement associated to it. So it's not that everything is just very much randomly, but they are also seeing each other, their spins, and they talk to each other. Okay? So one of the things is the absence of the ordinary magnetic order, so it doesn't want to order. Then there's going to be the fractionalized excitation, so the agent that talks between the spins and tells them that you're going to be entangled to each other, that agent is typically called spin-ons, okay? So if you had a classical case and you had a spin up, and then you would actually basically flip it, say, by neutrons, that spin up, when flips to spin down, it would produce a quasi-particle called a magnon, right? But then if you're having a single, if you have a case of a quantum spin liquid, that agent that talks between these fluctuating spins is basically a spin-on, a quasi-particle called spin-on, and the fact that those spin-ons is just like an electron with a spin and a half without the charge. So it's practically a fractionalized quasi-particle. And then you are going to basically have the long-range quantum entanglement, as I mentioned, in the quantum spin liquids. So it's beautiful, the theory is phenomenal, and it's very nice, but I would like to draw your attention to the very first signatures of quantum spin liquid is a lack of something. So you're not going to have an ordered state, right? But then that can complicate things, because if you're going to have a situation that your system doesn't show a long-range magnetic order, it can be a quantum spin liquid because it checks out the first priority. But then what can happen is that it can come because of something else. So experimentally probing quantum spin liquids and proving that you have an actual quantum spin liquid with entanglement in it is actually, it's very challenging. So today, we're going to look at some different techniques that are going to be complementary to each other for us to be able to understand this phenomenon a little bit better. Okay? So this is, for example, a picture that is showing the different ways that you can have entanglement or basically this, the bond between different sites. And one thing that I would like also to mention is that if you, for example, look at this particular pattern, you can see that the entanglement can be, or the valence bond can be along the shortest distance, or it can be along the longest distance. So what it means is that you have a unlimited amount of different ground states that they can basically are degenerate and they're providing you the full picture. Now, if you think about that, if I would want to break this site, right, this energy here, this bond here, I would require a lot of energy compared to if I would like to break this site that has a longer distance but is still entangled. But because I have infinite number of these situations, it means that the energy required to basically excite these states is going to be a continuous, right? So in case of if you had only one bond and then you were going to break that bond with, say, neutrons, you would have a particular range of energy that can do that. But if you have basically a continuum of excitations, then your neutron data is going to look like a continuum. Okay? So we're going to come back to this. So what are the experimental signatures of quantum spin liquids? So the first thing is the absence of long-range magnetic ordering. So if you're going to have a quantum spin liquid, one thing that you can quickly test is that the system does not order. But as I mentioned, this doesn't necessarily mean that you have a quantum spin liquid. You have a quantum spin liquid candidate. So if you look at all these papers that comes out, many people are very careful. They call this candidates because it's very challenging to prove that. So there's going to be, if you do a diffraction measurement, specifically with neutrons, right? Because neutrons can see the magnetic moment in the sample. So if there is no magnetic peak, then it says that that's one of the indications that you don't have a long-range ordering. Then, as I mentioned, you have to have a dynamic situation. So those spins are fluctuating. They're creating a lot of quantum fluctuations. They remain very dynamic. So that being dynamic itself is going to give us some information. For example, if you do NMR or mu-SR measurements, they will show the persistence of this dynamic situation in the sample. So I'm not going to get into too details about the mu-SR and NMR, but I will show you some other techniques that can also be used to make sure that our system stays dynamic down to lowest temperature. Then you have the fractional excitations, which I mentioned that you're going to have this continuum of spin-ons. So rather than having a very well-known dispersion associated with one band at a particular energy, you're going to have a continuum of excitations, which can actually be seen in inelastic neutron measurements. And then what else? So we can have unusual thermodynamic properties for quantum spin liquids. So what I mean by unusual, so these quantum spin liquids, depending on which group they belong to, they can have different thermodynamic properties. For example, specifically, if you want to think about it, specific heat is one example. So they can have if you fit their specific heat, which I'll show you later on, to a power law, it's going to give you a critical component that dictates which kind of a quantum spin liquid it belongs to, if any. Okay? And they also have, you can also see these type of properties from the magnetic susceptibility measurements. And then there are some more fancier techniques that can be used. For example, you can use thermal transport measurements. So for the thermal transport measurements, basically, it's going to give us information, is everything due to, because when we talk about the temperature, you talk about thermal fluctuations. So right away you think about phonons, right? So, but what I'm trying to say is that if you do the thermal transport measurements of quantum spin liquids, it's not only going to be the phonons that are now going to give us some information about the system. You have these spinons, in some cases a combination of a spinon and a magnon. So all of these is going to play a role in the thermal transport of the system. So that technique is also very important as a complementary technique to be able to understand if an actual candidate is a true quantum spin liquid, is it proximate to a quantum spin liquid, or it is basically not a quantum spin liquid, it's just a system that, for example, freezes into a particular pattern, and it's a spin glass, for example. Because if you think about it, if the system freezes into a particular pattern, it is not dynamic, but still it is disordered. So you're not going to see magnetic Bragg peaks if you try to measure that compound. Okay. So we talked about this. So there's going to be this sort of gauge fields that can be associated with that. So recently I have seen folks who are very much doing transport. So when you think about transport, you think about conductors and resistivity and these sort of things. But nowadays, actually, people are even looking at some quantum spin liquids candidates that are insulators, but still they try to do, for example, tunnel guide oscillator type of techniques, or try to do some other transport measurements to look at the quantum oscillations in these compounds. So this is also a technique that recently has been basically proposed as one of the ways that you can look at particular systems that they can have quantum spin liquid signatures to them. Also, quantum spin liquids can have topological orders, and now, entanglement and trying to say if a system is truly entangled is very challenging. But if you look at the literature these days, there's something called a quantum Fisher information. So based on some neutron scattering experiments in combination with that theory, people would be able to understand how much entanglement is associated with a particular pattern or particular spectrum of neutron scattering. Okay. So I would like to very quickly go over a couple of techniques just so that you have an understanding of what the data that we're going to show is going to represent. And so you all know about the DC susceptibility. So the DC susceptibility is not that complicated. So if you're going to have a particular peak, for example, going up and down, it indicates that you have an antiferromagnetic ordering. If it starts to shoot up as a function of temperature, it's a ferromagnetic ordering. However, if basically your DC susceptibility, even at very low temperatures, doesn't show any feature, any particular feature, that could be one of the indications that the system does not order. Okay? But that by itself is not enough. Because if you really want to look at the dynamics of the system, then something like AC susceptibility will become a little bit more important. So AC susceptibility is basically when you study the properties of the system, when you apply the AC magnetic field. So for the DC susceptibility, you apply DC field. For AC susceptibility, you apply an AC field. So you're going to deal with what is called a frequency, okay, because it's AC. Now, we're going to have a small alternating magnet, and it's going to be basically measuring the magnetic properties of the system, or M, as this magnetic field is oscillating. Okay? Now, the relationship that we're going to have between these two, M is going to be chi H, and so that is M, you're measuring M, you're applying H, and this is going to be the chi connection between them, the AC susceptibility. Now, for AC susceptibility, because you're dealing with AC field, you're going to have two components. You're going to have a real component, and you're going to have an imaginary component of the AC susceptibility. These two components are going to be key when we are trying to understand if a system stays dynamic, or if it freezes, or if it orders. Okay, I'll show you some data later on that you can see. So chi prime is typically what is called a real part of the AC susceptibility, and that's so the AC susceptibility is chi prime plus I chi double prime, and the chi double prime is the imaginary. So these are related to basically the phase that you have and the frequency that you're applying to the system. Now, how does a measurement work for the AC susceptibility? So for AC susceptibility, you're going to have an AC field, then you're going to have what is called a pickup coil. So in a pickup coil or a second coil, you have the sample, and that is going to be measuring what is going to be the change in the magnetization of the sample. Okay? There are applications, like you can look at the phase transitions, you can look at the dynamic properties, as I mentioned, and there are very good advantages. It's very sensitive. You can look at the different phases that come out of one system. Okay, so let's get back to quantum spin liquids again. So the one thing that you can do is just to measure the AC susceptibility, look at the real part of the AC susceptibility as a function of temperature. So typically what is going to happen is that you're going to have these different frequencies, right? So you can go from a small frequency to a larger frequency. The smaller the frequency, the more it becomes closer to the DC field, right? So in that case, your smallest frequency that you apply, it's as if you're looking at the linear response of the AC susceptibility. You can sort of compare that to the DC susceptibility. Now, when you start to change the frequency, you can see that, so here we are having these patterns, so it starts to show a peak, and this pattern is related to the relaxation time of your spins, okay? So if your spins are going to be frozen in a particular pattern, then when you start to change this frequency, you can see a slight shift in the peak of the AC susceptibility, because you're not going to have a unique relaxation time. You're going to have a multiple relaxation times because of the different spins that are oriented in a different way. Okay? Now, one way to say, so somebody may look at this data and right away say that, okay, it looks like that there is a frequency dependence to this AC susceptibility data at different temperatures, at different frequencies as a function of temperature, and this is the real part of it. So this could be indicative of you have a spin glass situation. But somebody may come and say that, no, I still think that I have a quantum spin liquid candidate. Be careful about that. So, and then what I would want to do is I want to see is the spins that are there are truly dynamic, because this could be coming from some orphan spins. When we deal with real world materials, what you know is that your spins are, or your materials are not going to be perfect. You may have site mixing, you may have site vacancies, so there may be some spins that are, for example, orphaned. Those spins can actually form a frozen situation, and that frozen state can actually induce a little bit of a change in the frequency dependence of AC susceptibility. The other way that you can look at this data is you sit at a particular temperature, preferably as low as possible, and then when you're at the lowest temperature, you can actually probe basically or change the frequency and look at the real and imaginary part of the AC susceptibility, okay? So when you do that, you're going to get a pattern. So if your pattern is gonna, and that pattern can be fitted to this formula, which is called the Cole equation. So this is actually quite an important equation. It's not as famous as the other equations like Curie-Weiss type of fitting and such, but it can give us some information about the dynamics. So here you're looking at the data plotted, real part of the AC susceptibility to the imaginary part of the AC susceptibility. And through this Cole plot, you would be able to plot, to fit the data that you have collected at different temperatures. Okay? So if you fit this data, there is this component alpha that comes out of this equation. If you have a single, basically, relaxation time, so if your system is dynamic, you would have one relaxation time, and that alpha is going to be close to zero. And when that happens, if you put the alpha close to zero in here, it's going to give you a circle, okay? But if you have multiple relaxation times, then in that case, you can think about the fact that, for example, you have a spin freezing or a spin glassy nature. In that situation, the alpha is going to be closer to 1. And if you put 1 in this equation, your pattern is basically going to be very flat. So in these two cases, you have either a semicircle or you are going to have a very flat, basically, data set. So that would be a very good indication of either you have a dynamic system or you're going to have a spin freezing or basically a spin glassy nature. So in addition to other techniques that we do, I recommend for us to definitely take this seriously as well and look at this type of measurements to make sure that the system, is it dynamic or it's going to be freezing, okay? Now, of course, the other technique that is very typical that we can do is the heat capacity measurement. So you can do heat capacity measurements through different techniques. So you all know what a heat capacity is. So the heat capacity is basically when you apply an amount of heat to basically your sample, and then you start to see how much its temperature is changing. It's basically defined as a heat capacity. Now, there are different ways that you can measure heat capacity. So if you have seen MPPMS, I don't know if you had the tour yet, right? So if you see most of the ones that are commercially available, they have a different technique. Some people make the heat capacity probe themselves. So there are different techniques that you will be able to do that. So there is one which is called the heat pulse method. So with the heat pulse method, what will happen is that you're going to give a known amount of heat to the sample, and then you're going to see how much temperature of the sample is going to change. There is one which is called the relaxation method. So with the relaxation method, what you're going to do is that you're going to heat up the sample, and then you're going to wait for it to cool down. And that time is going to give us information about the heat capacity of the system. Okay? The rate that the temperature changes. Now, the next thing is the adiabatic basically technique. So through this technique, your sample is going to be thermally isolated, and then it's basically all heat input goes into changing the temperature of the sample. So that's one of the, so it's more challenging. But if, for example, you're looking at a compound that has magnetocaloric effects in it, that would be a good technique to do the heat capacity based on this. There are various different applications, for example, for the phase transitions, structural or magnetic. So if you, for example, see a peak in your heat capacity and you're not quite sure if it's going to be magnetic or a structural as a function of temperature, what you can do is, for example, you can apply field and to see what the magnetic field is doing. If it's purely structural, it should not change. Your zero field should be the same as your finite field. But if it starts to show some sort of a pattern as a function of field, then it is going to give us some information that there's going to be some magnetic component into this phase. Okay? Now, let's go back to quantum spin liquids. So quantum spin liquids, depending on what kind of a group they belong to, the most two famous groups that quantum spin liquids belong to are either a spin-on Fermi surface or Dirac quantum spin liquids. Okay? These also have different situations. They can be gapless or gapped. I'm not going to get into too much details about that. Let's, as an experimentalist, let's just look at the data and see what we can observe off of the specific heat measurement of a quantum spin liquid candidate. So here, if you look at this, this is the heat capacity measurement done on a compound terbium magnesium gallium oxide. I will call this 1114 because so you can see there are ones and then there is a 4. So this compound, when actually it was originally proposed as a quantum spin liquid, they talked about the fact that this can be spin-on Fermi surface spin liquid. And the reason for that was they looked at the specific heat of the data of their measurement. Of course, when you apply field, there is something happening. So okay, checks out that there's going to be some magnetic component associated with that. And then what also happens is that you can see that there is going to be some dependence at low temperatures as a function of field. That low temperature tail is key for us to understand what kind of a quantum spin liquid, if any, we are going to have. So here, for example, you can see that they fitted this to a power law, and the power law component that they got off of this is close to 1. So it is saying that your specific heat as a function of temperature has a linear relationship. So if you have a linear relationship, according to the theory, it has more coordination with the spin-on Fermi surface. But then you can also have another component, another way to look at the data. For example, in this case, which is for a Kagame system, you can see that when, okay, one thing that I would like in brackets to open up is that typically when you do the specific heat measurements at very low temperatures, not only you see the magnetic contributions from the spins, but you have a nucleus, which that nucleus also has spins, and those spins can also contribute to the specific heat at very low temperatures, okay? So you see that here for this particular quantum spin liquid candidate, they have seen the data and it was starting to go down, but then it jumped up a little bit. That upturn at very low temperatures, it is due to the basically nuclear spin hyperfine interaction, okay? So you can actually calculate this and basically subtract it off. So when they have subtracted it off, they started to see something like this. And in here, you can see that they plotted C over T as a function of T. And you can see that it becomes linear, so it means that your specific heat has a T squared relationship as a function of temperature, right? So if it has a T squared relationship as a function of temperature, this goes with the theory that this says that this is a direct quantum spin liquid candidate. Okay? So, and if you see some sort of a sharp peak, a lambda type peak or anything like that, that could be an indication that you have either an ordered state or not. But if you have a sample in your hand and if you want to test to see with a specific heat, is it going to be a quantum spin liquid, you can put it in the PPMS, measure the specific heat, apply field, see if it has any sort of an interaction to that, and then how it behaves as it gets close to the zero temperature. Okay? Okay. Now, the most fancy way to also try to probe spin liquids is with the spectroscopy, okay? So you can see that there are different ways of that you can do that, and there are very high-profile papers that come off of this, talking about how, for example, neutron scattering can be used to probe quantum spin liquids. Now, what I would like to very briefly tell you about this, so we had this in the previous talk as well, I'm sure you have seen something similar to this slide forever, but let's just go over that. So if you're thinking about the neutrons, so the neutrons are neutral, so they can penetrate into the sample, so they can be a bulk measurement, but also neutrons, they have spins. So the spin of a neutron can actually interact with the spin of your basically sample, and through the dipole-dipole interaction, you will be able to measure the magnetic properties of the compound. So nowadays, there are different ways you can also do X-rays. So first of all, X-ray is basically having a negative charge. So it will see the negative charge of your compound as well, so it wouldn't be able to penetrate almost all the way to the sample, right? So it will see a lot of repulsion. So it's better for thin samples or for surface studies. But nowadays, just know that there are magnetic X-ray scattering that you can see sit as a particular resonance of your sample, and then tune your X-ray energy, and you will be able to look at some magnetic properties of that as well. But I'm going to focus on neutron scattering at this because it's bulk and it is easier, and I'm more familiar with it, to be honest. Okay? Now, so if you think about the neutron scattering, so there's going to be an incident beam, and then it will basically get reflected, and then you're going to basically measure this Ki and Kf. So the K is the wave vector, or the momentum of basically the beam. And if you have an elastic scattering, then your basically EI and EF are going to be the same. So if you have a single crystal and it has some particular orientation in the spins, you would be able to pick that orientation and you would be able to see that. You can also do that for powders. So you can have a powder, but instead of, in a powder, remember, it's as if you have a million of different single crystals oriented randomly. So instead of seeing one peak, one Bragg peak, you will see these rings that are associated with different peaks, Bragg positions. Okay? But then if you think about the inelastic, so let's start with the elastic first. So the elastic for elastic scattering, so you can look at the nuclear scattering, for example. So the beam is going to come in and then it gets reflected. And if you satisfy the Bragg condition, it's going to give us the peak. You would be able to see where these nucleus are sitting. So it's going to give us information about the structure of the compound. But also, you would be able to, for example, measure the magnetic properties of it, right? So if the spins are, if the beam is going to come in, and if the spins are oriented along a particular direction, and it gets out, your momentum transfer, or Q, is going to be basically the Ki minus Kf, so it's going to be along this direction. Now, for the magnetic scattering, remember that the neutrons will be able to only probe the component of the magnetic moment of the compound that is going to be perpendicular to Q. So if you look at this particular case, because Q and the moment are going to be along one direction, you won't be able to see any magnetic Bragg peaks in here. But here you would be able to see that. So lack of magnetic Bragg peak, if you're looking at the single crystal neutron diffraction measurement, lack of it by itself is not enough. You have to actually rotate the sample or rotate the beam or do something to make sure that it's not going to be along that particular direction. Okay? Now, we can also have inelastic scattering. So with an elastic scattering, the energy of the neutron is enough for us to excite the spin energies. So For example, for X-ray, we have kilo-electron volt, and the energy excitations in the compounds are typically milli-electron volt. That's why it's a little bit challenging to do, for example, inelastic X-ray and to probe magnetism. It's good for phonons, but for magnetism can become a little bit challenging. But in the case of neutrons, what you can do is basically you can tune the energy of a neutron to milli-electron volt, and then it can go in and see everything very well. And if it loses energy or gains some energy, it is comparable, so you would be able to calculate that. Okay? And then, so again, you're going to have elastic or inelastic. So this is inelastic, so you're basically, you will have some energy that is going to be transferred or gained from the sample, and then your Q is going to be your momentum transfer. Okay. Now, let's look at some data for inelastic neutron experiments on some quantum spin liquid candidates. So you're going to have basically, we talked about this, that you're going to have the data, which here you can see this is the energy, and this is Q. This is the momentum transfer, and this is the energy transfer. This is delta E. So what you can see in this particular case is that, for example, there is this excitation, but it shows a continuous excitation. So that could be a good indication that your system is going to be a quantum spin liquid candidate, rather than having one sharp band or a very dispersive band along a particular energy. And you can, of course, make a different cut and see in the, so this is a QQ cut. So they have cut a particular energy in here, and they looked at the excitation in the lattice so that they would be able to probe where these excitations are coming from. So one thing that I would like to know is that if you put your sample in the neutron beam and you see continuous of excitations, but it doesn't have any Q dependence to it, so it's very broad across all Q, that's typically not a good news. That could be an indication that you have like site mixing or chemical disorder in the compound that prevents the system from ordering, but also it is mimicking what a quantum spin liquid would do, but it's broad everywhere. So typically when you have a quantum spin liquid candidate, either it is a spin-on Fermi surface or it's a direct quantum spin liquid, you're going to have a particular Q dependence to that. Okay? So here, this is a very nice one because they have seen that there is some Q dependence to that, even though I have to say for this particular compound, which is a Kagome compound, there are some now discussions that there may be some disorder is playing a role, but it is one of the viable candidates. The other one that here, for example, I'm showing you, so for this, again, a Kagome system, this is also an indication that there can be some sort of a Dirac quantum spin liquid. So when I say the Dirac, so you will see that this is a reciprocal lattice. These are the Dirac cones, or where the spin-ons are basically going to shoot up in energy. And here you can see that they have seen very nicely in their data that there's first a continuum of excitation. Second, it's showing basically at the particular wave vectors that's corresponding to this picture for the Dirac cones. Okay? So these are the ways that you would be able to see the data and then be able to analyze it and figure out if it's going to be a quantum spin liquid or not. Now, I mentioned that if you cool down a compound to the low enough temperatures, if it orders, typically it is not a quantum spin liquid candidate. There have been some ideas out there, specifically for a Kitaev systems, that even though at zero field, you're going to have some sort of an ordering, but there may be other ways that you can induce quantum spin liquid state into this compound. And one of the examples is this particular compound, which is a Kitaev system. So this is ruthenium trichloride, and you can see that there is a phase diagram associated with that. But they say that at low temperature, if you don't apply any magnetic field, it has some sort of a zigzag ordering. An indication of that is basically shown in here. So you can see that there is a very clear, defined dispersion associated for this type of ordering. But then when we apply fields, I think this is around 7 to 8 Tesla, you can see that this feature, this dispersion, and rather narrow feature is gone, and then you will deal with this continuum of excitation that could be an indication that you have a quantum spin liquid. In this particular case, I would like also to note that not only side vacancies and side mixing, but also if you have a two-dimensional system or quasi-two-dimensional system, basically the way that these layers are going to be sitting on top of each other, if they are going to have some sort of an angle, So stacking fault, it is called. That can also induce something related to what we think a quantum spin liquid can see. And for this ruthenium trichloride, there is this stacking fault, unfortunately, so it complicates the picture a little bit more. Okay? Now, I would like to show you this particular compound because this compound, which again, this is the ytterbium magnesium gallium oxide. So this particular compound, you can see that it has a site mixing between the, I'm practically blind, so I won't be able to see much in here, but between the gallium and magnesium, there's a 50%, 50% site mixing. So here, basically, you're looking at this layer. So you can either have a gallium or you can have magnesium. Side mixing. So you can see that they plotted this very nice, they probed this very nice inelastic neutron experiment on this compound, and they saw this excitation continuum at particular Q points. But then, what happened was that when they applied field, so imagine you have a dynamic state. When you apply field, you're gonna eventually, hopefully, if the interactions are not too strong, you have with a conventional magnet at a neutron source, for example, by 8 Tesla, you would be able to polarize all the spins along a particular direction, right? So you're as if you're dealing with a ferromagnetic situation, so everything is polarized. So in that case, you're going to expect to see a very sharp and very thin, basically dispersion of the excitation. So this excitation is now basically applied onto this ordered, magnetically induced polarized ordered state, okay? But what they saw was that there is this basically continuous situation also happening here. This is very broad. So this actually triggered a lot of conversations. I can tell you within the 3 years or 4 years, there have been more than 400 papers on this compound or something related to this compound that talked about the fact that if you have site mixing, maybe it is not a quantum spin liquid, and here is your evidence that instead of having a sharp, basically dispersion at a high field, you're having a broad continuum, so you have this turbulence of electronic structure because of this site mixing. So one thing that somebody can do, in this case, they can actually do the thermal transport measurements. So thermal conductivity would be a good indication. As I mentioned, when you think about thermal conductivity, you're basically going to apply a heat pulse, and then you're going to look to see at one side of the sample, and then you're going to see how much the heat is being transferred through the sample. So, this probably you already know, but then the point I would like to make is that for this compound and for a compound that was close to this, so instead of magnesium they use zinc, in this particular case what they have done is the thermal conductivity measurements. So if you have only phonons and if you go to 0 temperature, you would expect the thermal conductivity to go to 0, right? Because there's no phonons, there's no temperature, there's no phonons. So the thermal conductivity, but there are no agents that can actually transfer the energy, the thermal energy. But if you have spinons or magnons, that's a different scenario. In those cases, what you can have is basically a plateauing of the thermal conductivity at very low temperatures. In this particular case, when they actually looked at the thermal conductivity, they saw that the thermal conductivity for these compounds actually starts to go down and it crosses the 0. So this is an indication that maybe this is not truly a quantum spin liquid candidate. I would like to open another bracket, which makes things even more interesting, is that if your system is still dynamic and you have spin-ons, but your spin-ons are very much slow, so it's not a very fast dynamic, that can also create what is called a scattering in the compound, and that can also induce something related to that. But then that data should be different than the data for a non-magnetic isostructure of your compound. So for example, I have ytterbium, magnesium, gallium oxide. Ytterbium is my magnetic component, but if I change ytterbium with lutetium, for example, lutetium is non-magnetic. They both have the same structure, and I can measure the thermal conductivity for both compounds, but what will happen is that if they are truly just due to the phonons, that both of them are going to have the same behavior, which is basically what they have done in here. So you can see that they are basically having a very much similar behavior and they go to 0. And also they have looked at the AC susceptibility, even though they have not done the cold plot, so that would be interesting. And then here's an example of a thermal conductivity for a quantum spin liquid candidate, which this is what I'm talking about. You can see here, this is for a magnetic compound, and this is for a non-magnetic compound. And you can see that it starts to basically give us a finite value as we go to the lowest temperature, and here is for another one that you can see that it plateaus on. So this is indicating that even though you're at 0 temperature, but you're going to have basically spin-ons or magnons that are contributing to the thermal conductivity. And with that, I would like to conclude that for looking at the frustrated systems, you are going to look to see how interesting they are based on the dimensions of that. Beside that, there are experimental signatures for them, but not only one experimental signature is going to be enough. Nowadays, we know that you have to have a collection of different experimental signatures along with the theoretical, basically, contributions, so that for us to be able to understand these systems and this very exciting and beautiful state better. Thank you for your attention.
Okay, questions? With quantum spin liquids being essentially an unstable equilibrium situation, are they very sensitive to the like crystal quality?
Yes, they are extremely sensitive.
So I was wondering if you could maybe not prove something's a quantum spin liquid, but help yourself like guide your own like figuring out where to look by, let's say you have two crystals, a bad quality one and a good quality one. You measure the good quality one, and you see more of a shift in the AC susceptibility from the good
For the
quality.
good quality one, you won't be able to see, you don't want to see a bigger shift. For a bad quality one, you probably will see a bigger shift in the AC susceptibility. So if you don't have, as a function of, so we are talking about the real part of the AC susceptibility as a function of temperature at a different frequencies, right? So you would see a peak, and then you change the frequency, and that peak starts to move a little bit, right? So if that movement is a lot, it means that you have multiple relaxation times. So you have different domains that they have created this glass region. But if you have a very dynamic situation, there's not going to be as much. So with that measurement on your two samples, you would be able to see which one is closer to be an actual equivalent speed.
Okay, but so I might be misunderstanding something, because I thought two sources of shift to a shift in the AC susceptibility. One could be static problems of just the orphan spins,
Yes.
which would just be from bad crystal quality.
Yes.
Whereas the other would be from the quantum spin liquid.
No. For quantum spin liquid, you really don't want to see a lot of, you want to have a unique relaxation time. And one way to do that, again, is the cold plot. If you look at the real and imaginary part of the susceptibility and fit that data, are you going to get alpha close to 0 or a unique relaxation time, or you're going to get closer to alpha equal to 1, which is going to be a distribution of the relaxation times.
I see. Thank you.
In your the specific process temperature measurements, you describe like the linear dependence can extend the spin on Fermi surface. Can you go back to the plot, or like from that? Like, I was trying to understand how you can infer that from the specific heat plot. How you get that?
So as I mentioned, so from the theory, your specific heat is going to have a power law associated with that. So if depending on what component of the power law you will get, if it's, so the one thing is that, so first of all, it doesn't show any sharp feature or anything like that. The specific heat also tries to go to 0 at 0 field. And then it will have either the power law relationship, either it's going to give you a linear for a spin-on Fermi surface, or a Dirac, for a quadratic for a Dirac. One other thing that's important is when you start to apply magnetic field, which I didn't say, For a direct quantum spin liquid, basically the specific heat starts to go up. So at higher fields, it starts to give some sort of, and again, there is, I can give you the reference for that. There's a very nice paper by Patrick Lee that talks about the fact that how they are related and how this basically, how the spinons are contributing to the specific heat and why the magnetic field can change.
Is there a question up here?
They want to go for a coffee break.
Okay, so everybody understands how to identify a quantum spin liquid now, right?
We hope, right?
Quantum spin liquids are very controversial,
Yes.
and it's actually a nice way to go into the next session after the coffee break. Discussion about ethics.
Yes.
So yes, please.
I don't have a doubt, but I just wanted to read the one which you explained in one of the slides where it was the elastic scattering, and there was one diagram and then that's like
This one?
and just the previous one.
The previous.
Yes,
Right.
yes.
Mm-hmm.
This. Yeah, and there's a diagram.
Right. So this diagram is basically for a powder sample, basically. So it's as if you have a lot of different tiny single crystals, right? So each of them is oriented differently, so it's going to give you the graphic and the different, basically, and a detector at the different area of it. But if it's coming from the same D or the spacing, it's going to be all of them sitting on one basically circle. So the radius of this circle depends on which reflection is giving you these brackets. So if you had only one single crystal, it would give you one peak and one particular truth area, okay? And in your area detector, you would see only one point. But if you have a powder or a polycrystal, it's going to give you these circles.
Yeah, just remember, we will provide all the presentations and most of the videos at some point later. All right, so let's thank Sara.